So first we'll start with a little review just from what we did last week with the neighborhoods. So just to consider the most basic of sequences 1 over n. And when you're doing these, it's always a good idea to think about what they look like, especially if it's a very simple calculation like 1 over n. That just means the first term where we start. All right, you plug in 1. All right, plug in 1, you get an answer of 1. So the first term is at 1. And you plug in 2, you get an answer of 1/2, 1 over 2, right? So if you just keep this pattern going, you can see it just gets closer and closer and closer to 0, but never actually equals 0. So we called that a limit, right? Something that it approaches but never actually equals. So the limit appears to be 0, right? And then we said, well, we could look at some neighborhoods that are really close to this limit, like 1/10 or 1/200th away, and find out, well, what value of n, or what term, what number term, is it the 13th term, the 44th term, that actually enters that neighborhood, right, given that little value, right, that little tiny window. So we did some calculations, right, in order to do this properly, and it looks something like this. All right, we said we have a lower bound of -1/10. All right, and then we have our sequence 1 over n, and we have an upper bound, right? So we had a lower bound, upper bound, because this sequence could enter either from the top or the bottom. If you look at this, you can kind of tell that if we have this neighborhood here, right, that it is going to enter from the top, right? It's going to starts up above and it starts getting decreases as you go along. So we expect, to find our answer basically on the second inequality because of that. Whereas if it was increasing from the bottom, it would enter at this boundary level and it would be the first inequality that would give us our value. But in either case, we just solve both of them just to make sure. So we have this one right here. Solve that one independently. All right, -1/10 is less than n, 1 over n. And you got to watch out for your rules for all your, multiplying by negatives and whatnot. But as long as you did that, you're okay. So if I solve for this, I'd have -n less than 10. And then when I solve for n, it becomes greater than -10. So that's just all of this. And then we have the second one, right, with the upper bound, and solve that separately. Right, so now we have 1 over n is less than 1/10. And then we solve this, we have 10 is less than n, which is the same as n is greater than 10. Right, so that second inequality is based upon just solving that. So we always solve them independently, expecting an answer from one of them, just depending on where it enters, from the top or from the bottom. Right? This one, of course, from the top. So this is the answer, n greater than 10. That makes sense. And this does not make sense right here because, remember, n is these numbers right here, right? 1, 2, 3, 4. These are the numbers of terms. There's no such thing as the -10 term or -9th term. So when we get an answer like this, we tend to ignore it because it does not make sense in context of the problem. Right? And therefore, we have our single answer, which just says all the values or all the terms that are above or bigger than the 10th term, right, are going to be in the neighborhood, right? So actually, from this, we derive a real answer of starting at the 11th term and everything bigger than that. Those are the terms that are inside. And you had to watch the directions. Sometimes it said, what is the first term inside the neighborhood? Or like this one says, what are the remaining terms? So it's all the 11th term and everything bigger than that are actually in the neighborhood. So you didn't have to go very far, right? Only to the 11th term to get within 1/10 of 0, within 1/10 of the limit, right? But if we start increasing, or actually decreasing that limit, that little, how far we want to be from the limit anyway, like instead of 1/10, go something much smaller to 1/200th, right? That's a much smaller window, so it takes longer to get there. So you could rework this whole thing and do the same thing over again. All right, solve this. All right. However, since we already did use this function or use this sequence one time, I already know the first one is still going to be the same thing, and it's not going to work out. So I could just skip over here and say, well, instead of 1 over 10, just make it 1 over 200. So let's try it with 1 over 200. And we get an answer, of course, that's very similar to the one we already had. So if we want to be within 1/200th, that means we have to have the 201st term or higher. So, whoa, where did it go? There we go. So, what we want to do really is develop a system where instead of having to plug things back in and, oh, this time to be within 1/10th, it's I need the 11th term or bigger, and then redo the whole problem to be within 200, I need the 201st term or bigger, right? I want to have a faster way of doing that, and that's kind of what we're doing today, is finding a more general formula that I could just plug in my epsilon, which is this number, that's how far we are from the limit. I can just plug it into some formula and figure out the n without having to redo the inequality solving over and over and over. So it's kind of like a general formula that we're going to figure out, okay? So we're going to change up a little terms, right? We talked about the general neighborhood, but we've also now talked about limits, and you've heard me say epsilon. So it's going to look very similar to what we did before, whereas a function will bounce back and forth and get closer and closer and closer to a limit, right? And we want to be within, we're going to call that L. This is called the limit. I think it was called P before, for the neighborhood, but we'll call this the limit. And we're going to have some value that's going to get really, really close to this limit, right? And we're going to call that, this distance here, epsilon. And it's like a little backwards 3. So that this value right here is just above the limit a little bit, and this is just below. It's kind of like that lower and upper bounds we were already talking about. So it looks very familiar. It looks pretty much the same thing, just different letters being used. And we want to get these two to be as close as possible, right? Close as possible. So that's why we use these fancy Greek letters and everything to when we're doing limits, because it generalizes how close these can actually get, right? And ideally, we want to make epsilon as small as possible to get closer and closer to that limit. So we have this thing called definition of the limit. How do I know if my formula works? So we have this sequence, right? And we want these to be closer and closer and closer. So I want the distance between these to be as close as possible. So one way to do distance with math is you actually subtract the two. So the distance between my sequence, right, and its limit, right, they get closer and closer to each other, and distance, another way of doing that is absolute value. And I want that to be as small as possible, right? So less than epsilon. Smaller, small, small. So this is called the definition of a limit, and we can just use this to plug things in and solve. And it's going to look very similar. I mean, I know this looks different and it's a lot of new stuff, but what you're actually doing and solving is going to be very familiar. Okay, it's just the notation looks a little different from what you're used to seeing. So the way I'd use this, and you look at the definition, look at the directions and say, if it says use the definition, that means they want you to do this. Okay, so the way that looks like is that I just do the absolute value of my sequence. That's this one, right? It's always in the curly braces, so that's the part, 1 over n minus the limit, right? So when you're setting these up, it's important to know that whatever's right here will be right here, and whatever is right here for the limit, that'll be right here. It'll always be subtraction, it'll always be absolute value, and then on the right hand side you're going to have is less than epsilon. And what we're going to do is just solve this and do the two side by side just like we always do, but instead of having this 1/10 or 1/200th, you have this epsilon instead in its place. And that's going to give us a general formula that we can plug in any value of epsilon and it'll tell us what value of n will work for that particular problem. So for instance, this is just the same as the minus epsilon. I can simplify the middle to just 1 over n. This is the positive epsilon. And just like we did before, right, solve these one by one. So I'm going to solve this one first. So negative epsilon, you got to watch all your rules for inequality signs. Make sure we don't mess up on those. We can see, multiply both sides by n, divide both sides by this negative epsilon, and we'll get n greater than 1 over negative epsilon. Which, since n is a positive number, this doesn't help us a whole lot. Epsilon's always positive, so if I plug in any value for epsilon, it's going to give me something that is negative. So much like the first one, right? We're just going to end up throwing this out. Okay, and you notice that this is the same sequence, 1 over n, as we did up here. So it didn't work here. It also didn't work here. So we're expecting the next one, the upper bound, right, this one, to actually work. If I do 1 over n less than epsilon, and I solve this for n, you get 1 over epsilon is less than n. It's the same as if you flip it around, n is greater than 1 over epsilon. And this is a positive number. This is something we can actually work with. So I know it's a lot of letters floating around, but it gives us a general formula. The power of this is that I no longer have to redo everything to find out, well, what if I want an epsilon of 1/10 or 1/200th? And I don't have to resolve it. All I have to do is just plug in 1/10. 1 divided by 1/10 is 10. 1 divided by 1/200th is 200. So this gives me the value of n, or what the nth term I need that actually goes inside that neighborhood, without having to recalculate it over and over and over. If I want to try a bunch of different epsilons, right, I don't have to do that anymore. So it gives us just a general formula, and that's what we're looking for on these problems, is that general formula. So a lot of the same setup, a lot of the same steps. We still have two inequalities to do, just like before. It's just that we have, instead of having an actual number here, we use epsilon, and that gives us the what we're looking for. Okay?
Can you send this room?
So go ahead and try, let's see here. Let's try this one, set it up the same way. Now you want to set it up with this definition first. So on all these we want to set up first, and then write the compound inequality, and then do the solving. So it's like a three-step process. And even if the limit is 0, still go ahead and write that in. So by the end of it, you should have something that looks like this. So again, what this does is it tells us for this particular sequence, I can plug in any epsilon straight into this formula, and it'll give me this end value that we used to have to solve over and over and over. All right, without having to recalculate and redo a problem over and over, I can just plug the number I choose, whatever it is, to see how close it is. I can just plug it straight into here and have that end value immediately, instantly. Okay. And on your, well, along with your assignment, I am going to post a Desmos link that looks like this. Takes you to here. So you can actually see what's going on. So I can go through and change the function. Change the sequence here to 2 over n minus 1. Set the limit to 0. That's what it tells us it is. And then down here there's a place to actually put your formula. So I want 2 over epsilon plus 1. So right here I'll have 2 over epsilon plus 1. Right. When I zoom out, go find my sequence. There it is. And now I can see, like, I already have 1/10 in here, right? It's telling me by the calculation, what it's doing is taking this number, epsilon, that I choose, and it plugs it in here, and it tells me starting at the 21st term. And if I did everything right, when I go here and zoom in, it actually will be correct. You can see at the 21st term, right, we're at the gate. That means the 22nd term should be the first one inside. So the answer is everything greater or greater than equal to 22. So it's a 22nd term. But if I want to say, well, I want to be, instead of 1/10, I want to be 1/100th. I want to be even closer, 0.01. All I have to do is do that, and it gives me the 201. Right? So it easily calculates everything I need it to do, okay, without having to do a whole lot of work. So that's the power of having this particular formula and knowing how to find it. And I'll post this link so you can plug things in and actually see it working. So the most important thing about here is just understanding what your answer means. Like the math is just basic algebra, right? We're just solving inequalities. But when you get to the end, knowing what this is used for, right? That's the most important thing. Okay. All right, so we've got 2 more of these. Skip ahead. There's another page we're going to practice a little bit more on right here. So see if you can write the setup, write the statement first. If you get that written down correctly, right, that's most of the work, is just having that written properly. So see if you can write that now using the definition. You notice the directions say use the definition, so that's when you do everything we're about to do. If it doesn't say use the definition, then you don't do this, right? So sometimes we learn a new tool and we forget to learn when to use it. 5n minus 1, n plus 2, minus 5, and then go through, and you have to do a little bit more algebra on this one because of common denominators and things like that, but nothing we can't handle. I'm actually going to leave a little space here. Since we have n plus 2 over here, I need an n plus 2 top and bottom here. And I like to simplify everything before I actually break it up and do the 2 inequality solving. I like to simplify this as much as possible. So we'll have 5n minus 5n, so those kind of cancel out right there, that with that. And this will be negative 1 minus, and I have to distribute, which is 10. So negative 1 minus 10 is going to give me negative 11. So I got it broken down to something smaller. And then we can go ahead and actually do the inequalities now. So we have negative epsilon is less than negative 11 plus n plus 2 is less than epsilon, which just means in between. Right, we want to find where is this in between these two numbers. So we can do the first. Right, solve this one first. So that would be n plus 2 greater than negative 11 over negative epsilon, which those two negatives just cancel out. And then lastly, we can just subtract 2 on both sides. So we'll have n is going to be 11 over epsilon and then minus 2. I think there's a tool for that. Aha. There we go. Then go ahead and solve the other one. Right there. And then use your judgment to decide which one's the correct one. Alright, so between these two, which one should we actually hold on to? There we go. So of course, this has usually the ones with the negatives end up being the one we throw out because n has to be positive at all costs, right? N starts at 1, then 2, then 3, right? So anything with a negative implication usually means that that's out, right? We can't use it. So just keep that in mind that this n stands for what number term you're on. And it has to be, starts at 1 as that's the lowest number, and it only counts by increments of 1. So for this one, if I was going to check this, I just punch this in like so. 5n minus 1 over n plus 2. And I want my formula turned out to be 11 over epsilon minus 2. So I can change this to 11 over epsilon minus 2. My limit is 5, so I got to change this up to 5. Zoom out. And we can see we're approaching from the bottom. It's another reason why the first inequality turned out to be the correct one, because this is increasing as it goes up. And right now it's 1 over 100. It's saying the 1098th term will get you there. That means starting with the 1099th term, right? That's the one that'll actually be inside within 0.01 or 1/100th of the limit. And the, let's see here. And the smaller I make this, I can make this 500. right? Instantaneously, it gives me what term I need to jump to, which we couldn't do by graphing. It would take too long to graph. I don't think Desmos would even support going this far to the, 5,500 term. I don't think it'd be able to even do it. So we need to have formulas like this in case we can't calculate it all the way. So that's how I use that tool. Looks very similar, just have this epsilon instead of a fraction, right? And just finding a general formula instead of a specific answer. And then what's going to happen on the homework, they might say, after you get this, you might see afterwards, go ahead and plug in, what's the answer for 1 over 200 or 1 over 500? And you just plug those in separately into here and see what the end value turns out being. So that will be the next step that'll be on some of the problems. After you get this, then just plug it in and calculate. Right? All right, so try this last one, see how that goes. Let's try to do it from beginning to end. And we'll be set. Minus -2. And do take note of the algebra that I'm using here. Just using some basic algebra, so I know I could just like switch this with this. Right, so that's why it just gets solved in one step. Same thing over here. I'm just exchanging the n and the epsilon with one another, right? And then of course I want to write the inequality with the variable on the left, right? So you can use those tricks. It saves time, but if you want to write everything out or show it a different way, that's fine. But you don't have to write all the work out for me to show work. And not required. Okay. But if I ask you to explain what this means, or to plug in some numbers once you get it, right? So if it give you some, values of epsilon, so assume epsilon equal, find out what n equals is epsilon is 1 over 50 or 1 over 500. You know that you just plug it in here and calculate, right? And you might get n is greater than 500, and then the answer would be greater than or equal to 501, just like we've always been doing. So that just gives us a general formula to find any value of n without having to redo the problem all over again each time. Okay. All right. So there's a little homework assignment in the bottom right-hand corner. You can start with those. Those are in the book. You're going to add them to the previous homework actually, and then I'm also going to pass out a worksheet that you're going to work on tomorrow. Okay. But you can do it in any order you want. It's up to you. Okay. So those are coming right now.